Hello students, today in this lecture I am going to explain about the series Lcr circuit. Here this is a series Lcr circuit in which an inductor, this is the inductor, capacitor and resistor are connected in series across a source of AC EMF which is given by V equals to V naught sin omega t. Here V is the instantaneous value of voltage while V naught is the peak value of voltage. These things you know. Omega is the angular frequency of the AC. Omega equals to 2 pi f. That you know. In the previous lecture I have told everything. Let at any instant, since the voltage is AC, therefore the current which will be produced, that will also AC. So I have assumed that at any instant the current in the circuit is I, and what will be the frequency of variation of this current? It will be same as the frequency of variation of AC voltage. Frequency will remain same. So let at any instant current in the series Lcr circuit is I, and at that instant the potential difference across the inductor is VL, across capacitor it is VC, and across resistor it is VR. What will be the expressions of VL, VC and VR? So that you can see VL equals to I into XL, where XL is the inductive reactance. Inductive reactance, it is the obstruction offered by inductor in the flow of current. So VL equals to I into XL. XL is inductive reactance whose value is omega L equals to 2 pi FL. Means this obstruction increases with increase in the frequency. What is VC? It is the capacitive reactance which is given VC equals to I into XC, and here XC is the capacitive reactance which is the obstruction in the same way here like this. It is also the obstruction offered by capacitor in the flow of current, and its value is given by 1 upon omega C, that is equals to 1 upon 2 pi FC. What is F? F is the frequency of the AC and C is the capacitance. VR equals to I into R. What will be their units? So since reactance, as already I have told, reactance is a term similar to the resistance. So its unit is ohm. Whether it is XL or XC or R, all are having the same unit. But if we see the phase relationship of VL, VC, VR with the current I, their phase relationship with the current I, then we will find that all are different in phases with the current I. Their phases are not same with respect to the current. Here on a phasor diagram I have shown you. Here this is a phasor diagram, you can see here, and already you have studied in the previous videos. You have seen in the previous videos, I have told you. If you have not watched, then you watch those videos. So here across a resistor, potential difference is always in same phase with the current. There will be no phase difference between the potential difference across resistor and current. Both will be in same phase. In same phase means both will simultaneously become 0, simultaneously achieves the maximum value and simultaneously changes the direction. While the potential difference across inductor, it is leading to the current by a phase angle 90 degree, pi by 2. That's why here the phasor of current is in this direction, while the phasor of VL it is leading, therefore it is 90 degree ahead, means 90 degree in the anti-clockwise direction, while the phasor of VR will be along the phasor of current. Similarly, VC it is lagging behind with respect to the current by a phase angle 90 degree. So here the phasor of VC is drawn in the clockwise direction from the current's phasor. So what will be the resultant of VL and VC? Here we have assumed that the VL is greater than VC. It is also possible that VL is smaller than VC. So since VL is greater than VC, therefore XL will be greater than XC. And why? Because VL greater than VC equals to IXL greater than IXC. I you can cancel, so XL is greater than XC. So when VL is greater than VC, then you can see here resultant of VL and VC, it will be VL minus VC in the direction of VL. So here I have represented by this phasor. It's clear. They are resultant by this arrow. While, so what will be the net potential difference? Net potential difference will be the resultant of this and VR. So that you can find by completing the parallelogram. As already I have told, potential difference and current are scalar quantities. But in alternating current, in order to determine the total potential difference, we will treat them as phasors. And we will find their resultant exactly in the same way as we were doing in the vectors. So here the resultant of VL minus VC and VR, it can be found by completing the parallelogram. So you complete this rectangle, its diagonal will be the net potential difference. Diagonal V, it will be the net potential difference. And what will be its value? You can see here, since this will be equal to this, therefore it can be taken as VL minus VC, while this is VR. So by using Pythagoras theorem, V square equals to VR square plus VL minus VC ka whole square. This will be the net potential difference. Means net potential difference at any instant, it is given by this. Now we can substitute the values of VL, VC and VR. So as we know, VL is what? VL equals to I into XL. VC is I into XC. And VR is, it is I into R. So on substituting here, when you will substitute, it will be this. Now from this bracket you can take out I common. So since it is the, here there is the square of this bracket, so when you will take it out, it will be I square. Within bracket XL minus XC whole square plus I square R square. When you will take out I square common from the square root, it will be I. Here it will be equal to I. I within square root XL minus XC whole square plus R square. So this is equals to V. So what is V upon I? V upon I will be this thing. Now you can see here, you have seen here that when the voltage is V, when the voltage is V, you can see when the voltage is V, current is I. So what is V upon I? So you can say that it will be the resistance, but it is not actually resistance. Here this V upon I in Lcr circuit has been given a different name. And why it has been given a different name? Because this is producing resistance, while these two are producing reactance. It's clear? These two are producing reactance. This is a coil whose resistance is 0. It do not offer any resistance. It is producing reactance. Though reactance is also obstruction in the flow of current. It is also obstruction in the flow of current. So what will you name it? It is a combination of reactance and resistance. V upon I will be the combination of reactance and resistance. So a new name has been given to it, that is known as impedance, denoted by capital J. Denoted by capital J. So you can see here, Here what is V upon I? It is the impedance, that is impedance of the series LCR circuit. And what is impedance? It is the obstruction offered by LCR circuit in the flow of current. So you can write Z equals to within square root XL minus XC whole square plus R square. Now if you substitute the values of XL, XC, so XL equals to omega L, XC equals to 1 upon omega C, so Z equals to this. Now see here, there is one more thing. If you see here in the phasor diagram, you will find that the net put in a series LCR circuit, when the case is this, when VL is greater than VC, when XL is greater than XC, then at any instant net potential difference V across the LCR circuit will lead to the current I by what angle? Phi. By what angle? Phi. Here phi, this is the symbol of angle. It's clear? So in the series LCR circuit, when the case is this, then net potential difference at any instant will lead to the current by a phase difference phi, where tan phi will be equal to what? You can see here tan phi equals to this upon this, VL minus VC upon VR, VL minus VC upon VR. So see here phase difference between the voltage and current, it will be tan phi equals to VL minus VC upon VR. Now substituting the values of VL, VC and VR. So when you will substitute, what will happen? In numerator you take out I common. That I will be cancelled with the I which is present in the denominator. So tan phi equals to XL minus XC upon R. That is omega L minus 1 upon omega C divided by R. It's clear? Here the value of tan phi will come out positive. In case if it comes out negative, then what will be? Then you will see that net potential difference will lag behind to the current, which I am going to discuss now. In this case, you will find when VL is less than VC, then XL will be less than XC. Now VL is less than VC means the phasor of VL will be smaller in length, phasor of VC will be bigger in length. So what will be the net of VL and VC? It will be VC minus VL. It will be VC minus VL. You can see here. And in what direction? In the direction of VC. It's clear? While the phasor of VR is this. So what will be the net potential difference? So net potential difference can be found by completing the parallelogram. So this diagonal will represent the net potential difference. And here you will find that net potential difference will lag behind to the current by a phase angle phi. And in this case, tan phi will come out negative. Why it will come out negative? Because XL is smaller, XC is bigger, therefore it will be come out negative. So you will remember that if tan phi is positive, then it means the case is this. Net potential difference is leading to the current by a phase angle phi. But if tan phi comes out negative, then what will happen? The case will be this. It's clear. That's why sometimes we write it as, in place of taking minus sign, we take difference. Tan phi equals to, this way we write. We write it as tan phi equals to VL difference VC upon VR, or we write it as XL difference XC. Difference means the XL minus XC if XL is bigger, XC minus XL if XC is bigger. It's clear? So here rest of the formulae will remain same. So you know this, that in case of the series LCR circuit, impedance is given by this formula. Phase difference between voltage and current can be found by using these two formulae. It's clear. If tan phi is positive, then VL will be greater than VC, XL will be greater than XC, and the net potential difference V will lead to the current I by a phase difference phi. It's clear. Whatever be the values of V and I, the phase difference will always remain fixed. It's clear. So now see here. Here you can see some special cases. Here you can see this is the case 2. Case 2 I have already discussed. Now see the case 3. Case 3 is when XL is greater than XL is equal to XC. When XL is equal to XC, then how will you find it? It's clear. So see here, when XL is equal to XC, then VL will be equal to VC, because already I have told VL equals to I into XL, VC equals to I into XC, therefore VL will be equal to VC. If we represent everything on the phasor diagram, then you will find that these two phasors, which are for inductor and capacitor, both will be equal in length. So what will be their net potential difference? That will be 0. There will be no potential difference in this direction. It's clear. So what will be the overall potential difference? So overall potential difference, only this one is left, VR. Here only there will be VR. Therefore what will happen? Here this circuit will behave as a pure resistive circuit. Net potential difference in this case will be always in phase with the current I. In this case, net potential difference will be VR, which will be always in phase with the current I. It's clear. Circuit will behave as a pure resistive circuit. And one more thing, here we will find that the impedance will be minimum. And why it will become minimum? So you can see here, what is the formula of impedance? Z equals to within square root XL minus XC whole square plus R square. When both will become equal, what will happen? This term will vanish. XL minus XC whole square will become 0, and what is left? R. This is the minimum impedance. Means series LCR circuit will have the minimum impedance. It offers the minimum impedance when the inductive reactance and capacitive reactance are same. In this case, circuit will behave as a pure resistive circuit. The net potential difference will be equal to VR, which will be always in the same phase with the current I. So this is the case 3. So all the 3 cases I have discussed: when XL is greater than XC, when XL is smaller than XC, and when XL is equal to XC. Now see here one more thing. This is when impedance will become minimum. You can see here impedance will become minimum. When impedance will be minimum, then you will find that the current will become maximum. Because what is the formula of current? Current I equals to V upon Z. Now since the Z is having the minimum value, when the Z is having the minimum value, then current will be maximum. V upon Z minimum. And what is the Z minimum? It is R. Here it is R. So this is the case of electrical resonance in LCR circuit. Electrical resonance. In resonance, what happens? One of the parameter of that thing will, for example, in case of sound, so one of the parameter, that is amplitude, that increases. So here also, here one of the parameter is increasing, one of the parameter of LCR circuit is increasing, which is the current is increasing. So this is called the electrical resonance in LCR circuit. When it will take place? When XL and XC both are same. means both the reactances are same. It's clear. Then electrical resonance will take place and current in the LCR circuit at that instant will be maximum. So what is the condition of electrical resonance? You can see here already I told that when both the reactances are same, that is XL equals to XC. XL equals to omega L and XC equals to 1 upon omega C. When you will simplify, you will get omega square LC equals to 1. On multiplying this thing in this side, you will get this expression. Omega square LC equals to 1. So what will be omega square? 1 upon LC. Omega equals to 1 upon square root LC. As we know that omega equals to 2 pi f, where f is the frequency of AC in Hertz. Frequency of AC in Hertz, while omega is the angular frequency in radian per second. In radian per second, it is measured in Hertz, while this is in radian per second. So omega equals to 2 pi f, where f is what? It is the frequency of applied AC voltage. So 2 pi f equals to 1 upon root LC. So f equals to this. You bring 2 pi in the denominator. Now if you see this thing, this is the natural frequency of a LCR circuit when its resistance is 0 or it is negligible. There is a condition, because if the variations will be in during the flow of current, there is the loss of the energy. During the flow of current, there will be the loss of energy. Then frequency will be changed. So 1 upon 2 pi root LC, it is the natural frequency of LCR circuit when R is tending to 0 or R is equal to 0. As you have seen in case of the damped vibrations. What happens in the damped vibrations? In damped vibrations, amplitude gradually decreases because of the air resistance. And in that case, what will happen? Frequency will not be equal to the natural frequency. So in the same case, if value of R will be significant, then there will be the loss of energy in the circuit. When current will flow, this much energy will be converted into heat energy per unit time. And in that case, the variations of current, the value of current will not remain constant with time. With time, it will be decreasing. With time, the magnitude of current will decrease, means it will be like this. If we make the diagram, it will be like this. And in that case, frequency will not be equal to this. So this is the natural frequency of LCR circuit when R is tending to 0. This we represent by F naught. So see here we have started from the condition of electrical resonance. What is the condition of electrical resonance? XL equals to XC. And starting from here, we have reached at this. We have reached at F equals to this. Means F equals to F naught. F equals to F naught. Means in other way, we can say that the LCR circuit will be in the electrical resonance state when frequency of applied AC EMF is equal to the natural frequency of LCR circuit. It's clear? It will be equal to the natural frequency of LCR circuit. A LCR circuit will be in the electrical resonance condition. That is, when current in the circuit will be maximum. During that instant, XL will be equal to XC, or frequency of applied AC voltage will be equal to the natural frequency of LCR circuit. It's clear? Now see here, there is one triangle, impedance triangle. You can see here, as we know that this is the formula of impedance. So here we have taken XL minus XC in this side and R in this side. It's clear. You can see here, you will find that VL minus VC and VR both are perpendicular to each other. This is the VL minus VC and it is VR. It's clear. VL minus VC is this, therefore XL minus XC I have taken in this direction and R in this direction. So this is, you can see here, when this is XL minus XC and this is R. When you will join this, this will be the hypotenuse that will be given by square root XL minus XC whole square plus R square, which is the impedance. It's clear. From here, this will be the phase difference. Tan phi equals to XL minus XC upon R. This triangle we call as the impedance triangle. Impedance triangle. Now see here. Now we will discuss some special cases of Lcr circuit. So first one is the Lr circuit. Lr circuit means there is no capacitor, only there is the resistor. It will be like this. I have shown here. It is like this. This is the Lr circuit. And when there is Lr circuit, there is no capacitor. No capacitor. So here potential difference VL, which is leading to the current by what angle? By 90 degree. Here potential difference VR, which is in same phase as of I. So you can represent this way. VR and I both are in the same phase. VL is leading to the current by a phase angle phi. So what will be the net potential difference? That we can find by completing the parallelogram. Net potential difference will be represented by this diagonal. This will be equal to, this is VR and this you can take as, this one can be taken as VL. So it will be V square equals to VR square plus VL square. It's clear. This will be the net potential difference. So here we can see that net potential difference is leading to the current by a phase angle phi. It is leading to the current by a phase angle phi. Tan phi equals to VL upon VR. It is equal to VL upon VR. VL equals to IXL, VR equals to I into R. So XL upon R, that is omega L upon R. You can see from here once again. Tan phi will be equals to VL upon VR. We will not write VL upon I because here we have taken VL, so this will be VR. It's clear. So tan phi equals to XL upon R. That is omega L upon R. Means in the Lr circuit, net potential difference leading to the current by a phase angle phi, which is given by tan phi equals to omega L upon R. What will be the net potential difference? It will be given by this. Already you know this formula. Here if you see net potential difference, what is the formula? You can see here. You can remove VC. So it will be V equals to VL square plus VR square. It's clear. So here you will get the same thing, VL square plus VR square. What will be impedance? Impedance, now you can remove XC. See here, XL minus XC whole square plus R square, but there is no capacitor, therefore XC can be removed, therefore Z equals to XL square plus R square. That is, it can be written this way. Now CR circuit. In the CR circuit, there is no inductor, means there is only capacitor and resistor. This is C, this is R, this is VC, here it is VR. At any instant current is I when the voltage is V. So see here on the phasor diagram, you can see here VR and I are in the VR and I is in the same phase. VC is lagging behind to the current by a phase angle 90 degree. So what will be the resultant of VR and VC? That can be found by completing the parallelogram. It's clear. So V square equals to, here you can see V square equals to VR square plus VC square. In CR circuit, net potential difference lags behind the current by a phase angle phi. It is lagging behind to the current by a phase angle phi. And why it is lagging behind? Because in the clockwise direction with respect to the current phasor. With respect to the current phasor, it is in the clockwise direction. Therefore, lagging behind. If it is in the anti-clockwise direction from the current phasor, then leading. So, tan phi will be equal to what? Vc upon VR. Or we can find by that way Vc upon VR, that is Xc upon R. What is Xc? 1 upon omega c. So, tan phi equals to 1 upon omega c whole divided by R. Or V equals to, within square root we can write Vc square plus VR square. What will be the impedance? Impedance will be given by this formula. Here you will remove the XL. When you will remove the XL, or you substitute the values of here, when you will substitute, you will find that it will be IXC square plus I into R square. When you take out I common, it will be XC square plus R square. So, V upon I will be equal to XC square plus R square. That is the Z. That is the impedance. What will be the unit of impedance? That you know, it will be ohm. Now see here. Here there is one more case, LC circuit. And here we have taken a LC circuit in which you can see this is a coil whose resistance is 0. We have taken a coil whose resistance is 0. It is clear. This is capacitor, this is the inductor, and here this is the alternating voltage V. Current at any instant is I. It is clear. Here this is a resistance-less coil, though practically it is not possible. Practically it is not possible. Therefore, LC circuit only a conception. In reality, it don't exist. It is clear. So here you can see, here VL is leading to the current, VC is lagging behind, and here we have assumed that VL is greater than VC. So what will be the net potential difference? It will be VL minus VC in this direction. Suppose if VC is leading, then its phasor will be longer, arrow of the VL will be smaller, net potential difference will be VC minus VL in this direction. It is clear. So impedance in this case, what will be the impedance? So you can see here, as we know that the formula of impedance, it is XL minus XC whole square plus R square. Since R is 0 here, so what will be Z here? It will be XL minus XC, or we write it as XL difference XC. XL difference XC. So this is the LC circuit. Now after this,